Hello, my name is Don Metzger. This video is about the Analog Devices AD9081 MxFE chip and its ability to do phase coherent transmits and receives. We'll take a look at this feature using QIQ Systems quick MultiTransceiver software. Here's a quick overview of the video. First, we'll introduce the concept, why it's important to be able to do this phase coherence. Then we'll go and show the measurement setup, make a waveform for doing our testing. Then we'll do a couple of different measurements to show the phase coherence. Finally, we'll talk about where you can go to find some example code so that you can do this on your own. Here's a block diagram of the Analog Devices AD9081 MxFE chip. At the top, we can see the transmit side of the chip with the 4 DACs. And each one of those is fed by 4 main channelizers, or the coarse digital up converters. And then on the left-hand side are the fine digital up converters. Middle of the chip we have the receive part, which are the 4 ADCs. Each one of them feeds the coarse digital down conversion, and then some channelizers on the left-hand side of the receive side. So the issue that we're trying to address is that we have lots of local oscillators in this system. We have one in each of the 4 coarse digital up converters. We have one in each of the fine digital up converters. We have one in each of the coarse digital down converters and one in each of the fine digital down converters. And we need these local oscillators to be synchronized with respect to each other, not just in the way that they play out phase, but they have to start at the same phase and continue that relationship. So what we're going to be focusing on in this video is how to control those local oscillators, get them started in the same phase state, and then how do we see that? How do we confirm that that's the way that the chip is operating? This is an important issue if we're doing something like beamforming with the chip, because the local oscillators are setting the phase of each of our channels, and the phase is basically what we use to address beamforming issues. Here's our measurement setup. At the top, the green board is a Xilinx AMD ZCU102 host board that's connected to the network using a network cable. And then we have the AD9081 eval board, and then we're going to be connecting various things to the SMA inputs and outputs of the 9081 eval board. When I'm doing fine timing or phase or frequency analysis of some sort of a system, I like to use radar type waveforms. Radar waveforms are designed to give us a lot of information. So let's bring up Quick Generator and let's go to the LFM radar, linear frequency modulated radar signals. Let's go from minus 50 megahertz below the carrier to plus 50 megahertz above the carrier in 10 microseconds with a pulse interval of 20 microseconds. And our sample rate is 250 megasamples per second. That's the rate that the 9081 chip is expecting I&Q data coming in and going out. So we make it, then we go off and we save it somewhere so we can remember it and call it up in Quick MultiTransceiver. Okay, so we've made a waveform. Here's our first measurement setup. We have the DAC 0 output feeding the common leg of a 4-way splitter. Each of the outputs of the splitter is routed back around to the 4 ADC inputs on the eval board. Next, let's bring up our Quick MultiTransceiver software. First thing that we want to do after the windows open up is we want to select what it is that we want to see. So go up to Windows, Active Windows. I want to see the IQ waveforms. I'm going to look at a spectrogram and not the spectrum, and then I want to look at the correlation results that come out, and I want 4 plots because I'll be looking at 4 different channels here. So we do that and it rearranges the windows for us. Then we go over here to Instrument and we say we're going to be talking to a 9081 over the network, and here's the IP address for that Xilinx ZCU 102 board on the network. Then we want to go and select a transmitter file. So let's browse to that waveform that we just created. It's going to be down here, and here's the LFM 100 10 microsecond 250 megasample per second waveform. Call that, set that waveform, and then finally we want to go to the 9081 control, and let's start on the All tab. Let's take 20,000 received samples. On transmit number 1, we want to use that and transmit at a gigahertz. We're not going to transmit on the others at the moment. And then on the receive side, we want to receive at 1 gigahertz with all 4 of the channels over there. So everything's set up just right at this point. I like to go off and save my startup settings to remember this in case I have to come back and run this again later. Finally, we're going to run the correlating receiver on this. That's a good way to look at phase comparisons and so forth. So we need to tell it, here's your ideal waveform that you will be comparing all of these received channels to. Alright, let's just hit the start button and we start gathering data from the 9081. I'm going to stop it just so we can take a look at this a little easier. Each of the vertical columns is one of the ADC channels. So this is ADC 0, ADC 1, ADC 2, and ADC 3 over here. This is the time domain view of the data. This is joint time frequency, which allows us to see that chirp happening in frequency chirping up as time plays out. And then finally, the correlation result is down here at the bottom. The key thing to look at on the correlation plots, in the top left hand of each of the correlation plots, it's listing the max value for the correlation, which has a linear value of 0.94, and the LO phase is 89.1 degrees, the phase of the correlation at this peak here. And then we do a delta calculation of what's this phase as compared to the phase of the first channel over here. So this delta is 179.9 degrees. Why is there 179.9 degrees? Well, the splitter has different path lengths. Maybe the cables aren't quite the same length. There are various reasons why there might be phase differences between each of the channels. The key thing, though, that we want to know is that this relationship, this phase relationship, stays constant. If I go and start this again and run it for a while, that phase is staying lock solid at 179.9 degrees. And I can start it again, and it stays solid again. So what this is showing us is that phase relationship between the local oscillator doing ADC 1 and the local oscillator doing ADC 0 is staying the same through stops and starts. We can even go in here and change the frequency and make receiver number 2 go to 1.1 gigahertz. So let's totally mess up its phase. It's not going to correlate very well because it's off in frequency. You can see that. It's not doing a good job. Now let's go back and set it where it was before at 1 gigahertz. And start it up again, and boom, it hops right back to the 179.9 degrees of delta phase compared to this channel over here. So what this is telling us is that the 4 receive channels phase stays locked with regard to all of the other receive channels. So that's good if you're doing receiver beamforming. You want to have a consistent relationship between the phases of your channels. Here's our next measurement setup. In this case, we'll just loop each DAC output back to an ADC input. So DAC 0 to ADC 0, DAC 1 to ADC 1, and so forth. Back in QIQ MultiTransceiver, we need to tell the 9081 to output data from each of its DACs. So transmitter number 1 is on. Let's use transmitter number 2. Let's use transmitter number 3. And let's use transmitter number 4. Likewise, we have to make sure that we have a file ready to go for each of those transmitters. So we need to call up the same file for each of those transmitter files. Now we're ready to start it up, and there we go again. Again, I'll let it run for a little while and then I'll stop it. What we're seeing now is we're seeing this phase relationship is being driven by a DAC driving an ADC. And if we start and we stop and we start and we stop, that phase relationship is always the same. Our previous measurement convinced us that all 4 of the receiver channels LO stayed locked with respect to each other. What this is showing in addition to that is the 4 transmit DAC LOs are staying locked with respect to each other. As a final step in the process here, let's add some receiver waveform processing to get rid of that phase difference between the channels. So receiver channel 1, that's kind of our reference. Receiver channel 2, let's go in there, and his phase is minus 171.3, so let's add a positive 171.3 degrees of phase to receiver channel 2. Receiver channel 3 is 162.4, so let's make that minus 162.4. And then finally receiver channel 4 is minus 16.3, so let's make his phase positive 16.3. We'll rotate that. This is just an adjustment that's being done to the IQ data coming from the chip. We're not adjusting the phase in the chip. It could be done in the chip, but in this case we're just doing it with some waveform processing. Now you can go in and see that all of these phases are lined up and everything's at 0 phase. So it's just sort of a calibration step if you prefer to have all of these showing you the same numbers as opposed to each one having a different value. You can dial that in. As a final step, let me show you how you can do this for yourself. Go to the Analog Devices page on GitHub, and down at the bottom you do the View All repositories, and we're going to go into the Pi ADI IIO repository. So many people are doing Python out there these days, perhaps you are as well, that a lot of the best examples are being done with Pi ADI IIO. So there's under the examples folder, we can go down here and we can find AD9081 sync_start_example.py. So, and you can see the code in here that is used to do this synchronization. Basically, it's a bunch of IIO calls to get all of the phases aligned. Here we go. We're doing some GESD, setting some parameters in GESD. We're doing some arming of the syncs, and then we're doing some triggering of the syncs. That's what I use to create the synchronization in my software, although I'm not doing Python. You can still read through the example there and figure out the steps that you need to do this yourself. Alright, that's it for this video. You can visit us online at quicksystems.com or send us an email, sales@quicksystems.com. Have a good day.